Hi, I'm Debayan, and today, alongside Dr. Xiaoming Liu and Dr. Anil Jain from Michigan State University, we present to you FaceGuard, a self-supervised defense against adversarial face images. It has been shown that automated face recognition systems are vulnerable to adversarial attacks. That is, we can alter an input face image with small human imperceptible changes in a manner that can evade convolutional neural network-based AFR systems. Even when the perturbation is imperceptible to the human eye, recognition performance of state-of-the-art AFR systems drop. For instance, let's take a look at the image here. The top row denotes adversarial faces synthesized via 6 different adversarial attacks that are used in our study, while the bottom row shows corresponding adversarial perturbations where gray indicates no change from the input. Notice the diversity in these perturbations. We also show the arc face cosine similarity scores between the adversarial image and the unaltered input real image. A score above 0.36 here indicates that two faces are of the same subject. Therefore, none of the 6 adversarial face images successfully match the input real image. Quantitatively, this table shows that the performance of a state-of-the-art arc face matcher drops significantly when any of the 6 adversarial attacks are introduced. In order to defend against such attacks, there are 3 possible approaches identified in literature. Either we train a binary CNN detector that can distinguish between real and adversarial examples, or we attempt to revert the pixels or purify an adversarial image such that we can retrieve a real image back, or we train a new face recognition system with adversarial images as our training data, known as adversarial training. More concretely, here we see on the left that adversarial training degrades AFR performance of a face matcher called FaceNet on real face images in LFW dataset compared to the standard training on real images. Also, the problem with detectors is that a binary classifier trained to distinguish between real faces and FGSM often fails to detect an unseen attack type, namely projected gradient descent. Thereby, both of these methods grossly overfit to the adversarial examples. Unlike prior efforts, our proposed FaceGuard incorporates both an adversarial detector and an adversarial purifier. If the input image is detected to be adversarial, only then do we purify that image. Here's an overview of the training of the proposed FaceGuard in a self-supervised manner. An adversarial generator, G, continuously learns to synthesize challenging and diverse perturbations that evade a face matcher. At the same time, a detector, D, learns to distinguish between the synthesized adversarial faces and the real face images. Here, an adversarial face is denoted by X adversarial, which is the addition of the real image X and an adversarial mask, which is the output of our adversarial generator. Perturbations residing in the synthesized adversarial faces are then removed via purifier PUR. All of the 3 modules are being trained simultaneously, and they all learn from each other. An adversarial face generator should generate images that are visually realistic. It should also successfully evade face recognition systems, and it should also be stochastic such that we have a variation in the amount of adversarial perturbations. We propose an obfuscation loss which minimizes the cosine similarity between face features of the input image and the final adversarial image via a white box face matcher, let's say FaceNet. We also use a perturbation loss, which is a hinge loss that minimizes the norm of the adversarial mask such that the final results are visually realistic. We also propose a diversity loss to improve the stochasticity of the adversarial generator, where 2 input latents, Z1 and Z2, if they are different, then the adversarial images need to also be different. Finally, we introduce a adversarial GAN loss that improves the visual realism of the final adversarial image. Our proposed adversarial detector incorporates a binary cross-entropy loss for distinguishing between real and generated adversarial samples. And finally, the purifier objective is to recover the real face image X from a given adversarial image X adversarial. We aim to automatically remove adversarial perturbations by training another neural network, PUR, referred to as the adversarial purifier. The adversarial purification process can be viewed as an inverted procedure of adversarial image synthesis. Therefore, we have a feature recovery loss, which is the negative or the reverse of the obfuscation loss. We also have a perceptual loss that minimizes the difference between the final purified image and the input image, real image X. And we have a regularization on the purified image such that the overall purification process changes minimal pixels. Finally, we also incorporate our detector to guide the training of the purifier. Note that due to the diversity in the synthesized adversarial faces, the proposed detector learns a tight decision boundary around real faces. This can serve as a strong self-supervisory signal to the purifier for ensuring that the purified images belong to the real face distribution. Therefore, we also incorporate the detector as a discriminator for the purifier via the proposed bona fide loss. Detection accuracy of state-of-the-art adversarial face detectors in classifying 6 adversarial attacks that are synthesized for the LFW dataset are shown above. Detection threshold is set for 0.5 for all the methods. All baseline methods require training on pre-computed adversarial attacks on CASIA webface. On the other hand, the proposed FaceGuard is self-guided and generates adversarial attacks on the fly. Hence, it can be regarded as a black box defense system. Proposed FaceGuard outperforms all prior detection systems. It is also considered as the most generalizable detector since it has not directly seen any of the attacks above, but only seen the attacks generated by the adversarial synthesis method. We also take a look at the automated face recognition performance of ArcFace under no defense and when ArcFace is defended via the proposed FaceGuard and prevailing robustness or purification techniques. We see that, again, the proposed FaceGuard method completely outperforms prior efforts on purifying or adversarially training AFR systems. Also note that unlike prior efforts, our proposed FaceGuard also helps maintain the accuracy on real face images. Adversarial faces synthesized by FaceGuard during training. Note the diversity in perturbations within and across training iterations. In summary, we propose a new state-of-the-art adversarial face synthesis method that is highly transferable and stochastic and perturbs only the salient regions of the face. In addition, a generalizable adversarial face detector is also simultaneously trained that outperforms any prior efforts in detecting adversarial attacks. And lastly, we also train an adversarial purifier alongside the generator and the detector that enhances the face recognition performance of ArcFace from 34.27% true accept rate at 0.1% FAR under no defense to 77.46% true accept rate. Thank you.